is at home today because the childcare facility is low on how do you call the people looking after the children. So it's only half day. So I have to pick up at 12:30. So they're upstairs. So
but the university is open, I gather.
Yeah, absolutely. So that's not a problem.
But we don't have classes on direct classes.
Exactly. Yeah. So teaching is online.
We're allowed to go to the office, but not all together.
Yeah, Hopkins.
No, I don't touch experiments.
Hopkins started in-person classes on February 1st. Well, February 1st was out because of a snowstorm. So yesterday they started, and today will be a second day of classes.
Okay, that's ambitious.
All right, I believe I have to start, if you don't mind.
Yeah, we have
so let me,
15 people. Good.
Yeah, there's a few people I can see in there. You're a popular guy. So welcome everybody back to the online SPICE-SPIN+X seminars. As you guys all know, we organize the seminars from the Spin Phenomena Interdisciplinary Center that I lead together with Karen Evershore-Schitte, and in collaboration with the Collaborative Research Center of SPIN+X between Mainz and Kaiserslautern, led by Martina Schliemann and Burkhard Hillebrand in Kaiserslautern and Matthias Chloe here in Mainz. This is a webinar format, as you all know. Most of you are coming back all the time, so you know that you just simply watch the talk. And later on, please write your questions in the Q&A part, and then I will give the floor to you once the Q&A starts, or put your hand up, and then we will do that way. We have all the seminars always at 3 p.m. So far, the things are filling up for the semester nicely with a lot of very good lineup of speakers. And again, keep things professional if you don't mind. So far, it's been no problems at all. Today's speaker, just a few words. It's my pleasure to have Oleg Tchernyshyov to give the talk. He's been a well-known person in our community, very respected, with lots of very good perspectives, often not the traditional ones, which is really great, but very pedagogical in his talks, always. He, of course, like most Russians, came from the Moscow Institute of Physics and Technology. As I've known, I have lots of friends and colleagues from there, from Texas A&M. So all good physicists seem to come from there, and then has a very star career. And from 2002, I started in Johns Hopkins and has been there ever since. Now enjoying the snow in the weather. He has many awards. Of course, I just put a few here. He's an PS fellow. Since 2019, I'm a little shocked by that, because you definitely deserve to be a fellow from long before. You probably didn't get around sending the application or something. But fellow of the Japan Physical Society, and has had several career awards, etc. So with that, I don't want to delay the discussion, so I'll go ahead and give you the floor. Please share your screen again, Oleg, and start whenever you like.
Well, thank you very much, Jairo, for this nice introduction.
Okay.
It's a great pleasure to give a talk at the SPICE-X webinar, which is the place these days to go for spintronics talks.
Thank you. Well, it's also a very nice place, of course, we should say. Our colleagues in Nebraska that has organized also super talks there. We are combining very well to do that. So.
Yes, and then there is Daejeon and Keist in South Korea, where I'm giving a talk tonight.
Very good. So you can double it up. I hope it's the same talk or a different talk.
It's similar. It's a bit shorter. 40 minutes.
Good. At least you don't have to work so hard. Okay, I'll let you now start. Go ahead.
Well, I'm feeling as nervous as I was during my very first APS March meeting talk, seeing that we have 163 participants. Well, great audience. So thanks again, Jairo, for organizing this. I'm going to give my perspective on chiral magnetism. It's not entirely mine, in fact, but it's been in existence for a while, although most of us have not known about it. Let me acknowledge my collaborators, Daniel Hill, a postdoc who's working with me, and Valery Slastikov, an applied mathematician at the University of Bristol. I've discussed this with a number of people acknowledged here and benefited from attending programs in Aspen and KITP in Santa Barbara. And last but not least, thanks to the DOE for tolerating my work on this. Good. So the take-home message, in case you have to rush out the door and not hear the entire talk, this is about geometrization of chiral magnetic interactions. So we know what the standard perspective is on the chiral magnetism. It's been with us for 50 years plus. Chiral interactions, known as the Teleshinski-Mori terms, and that's where the twists of magnetization come from. And I will give you a different perspective on this, and instead of thinking about the energy, such as Teleshinski-Mori interactions, I'll say something about curvature of spin parallel transport. This has a very direct analogy in theory of relativity, where gravity is not treated as a force, but rather as an effect of geometry, curvature of parallel transport in space-time. And we'll discuss a simple model, the Heisenberg exchange interactions, just pure Heisenberg exchange, but in a curved space from the viewpoint of spins. So the advantage of this approach is, first, it's a different perspective. It's always useful to have a different perspective on things, as Kyra mentioned. But it allows you to easily extend the spin conservation law to situations where it's apparently broken from the old perspective. And it gives us new tools to explore things, as I will illustrate in this talk. So here's an overview of the talk. I'll introduce the Chiral ferromagnetism, the lattice and continuum descriptions, go over the spin parallel transport, and introduce an SO3 gauge field. And then we'll discuss the gauge Heisenberg model is a minimal model of the chiral ferromagnet. So there will be 3 applications presented. One is the extension of spin conservation. Another, a perspective on the recent theoretical prediction that a DM term can be induced by passing spin current through a sample. And then we'll have the probably the longest part of this, the application of this theory to Skyrmian crystal ground state in the 2-dimensional chiral ferromagnet. And if you're curious to see the details of this, there's a preprint on the web that you can read. So here's the minimal model on the lattice, which yields chiral magnetic states. You have exchange interactions, the dominant force, and you have the Teleshinski-Mori interaction, which is weaker. It's a relativistic effect of order V over C. So D is much smaller than J in a typical compound. And this was introduced by Mori back in 1960. Lattice models are awfully hard to solve. And so it's no surprise that the continuum description appeared shortly afterwards due to Teleshinski. And so we have the Teleshinski-Mori theory as a result. So here exchange is normalized to have strength of 1/2 and is expressed as just the gradient of magnetization squared. And the chiral DM interaction becomes linear in the magnetization gradient and proportional to some Teleshinski-Mori vectors. These are the strengths of the DM interaction. And the weakness of the spin-orbit coupling now indicates that these vectors have the magnitude in these units that is much smaller than the inverse lattice spacing. The symmetry of these, or the possible values of these DM vectors are restricted by the symmetry of the magnetic system. And in particular, if you have a cubic symmetry, such as we have in manganese silicide, then the Teleshinski-Mori term or vector for direction I is just pointing in that same direction and has the same strength kappa here. So if you put together these terms and perhaps add a Zeeman interaction then you get a rather rich phase diagram here shown for manganese silicide. And it has a helical phase at sufficiently low temperatures and low magnetic fields, a conical phase, and what used to be a mysterious A phase, which turned out to be the phase of the Skrimian crystal, as predicted by Bogdanov and Yablonsky in the 1980s and discovered by Christian Fleder's group in manganese silicide on the basis of neutron scattering. These days, we also have Skrimian crystals in thin films where they occupy a more extended portion of the phase diagram. These are beautiful real space images of Skrimians in one of these thin films. But this audience needs no introduction to Skrimians, so let me jump to explaining what my geometric perspective is on this. So I think there is a question.
No, don't worry about it. I will monitor that. It's just that Barney doesn't have audio for some reason. I will monitor those. Don't have to interrupt during the time.
Perfect. Will do. Keep me on time, Hira, please.
No
problem. Let's consider the spin parallel transport. In the simplest setting, you start at some point with a spin pointing, let's say, up, and you move it to another point in space, just keeping it parallel to itself. Then you can move it in a different direction and then keep it parallel to itself. And then you can complete this contour, or you can move the same spin to the same point along two different trajectories. And in the simplest case, the result will be the same. You will still have a vector of spin pointing up. And that's what I call the trivial spin parallel transport. That is, transporting a spin along two different paths gives you the same final orientation. But the parallel transport need not be that simple. And here's a twisted version of parallel transport. So the rule is you move a spin in the spatial direction x while twisting about the x-axis, and you move it along y while twisting the spin along the y-axis at the same rate kappa. So as a result, the orientation of spin changes in this global frame. And an interesting effect happens if you follow two different paths. So for this path, you have one orientation of the spin in the end, and for that path, you have a different orientation of the spin. And so they will be slightly mismatched in proportion to the area of this loop. Here you can define a gauge field that AX and AY that expresses the rate at which the spin twists going this way and that way. And the final mismatch of the angles between these two trajectories is proportional to the area, ds, and a vector f, which is what we'll call the SO3 gauge curvature, or the SO3 non-abelian magnetic field, which is related to the gauge potential in this way. So partial IAJ minus partial JAI is a familiar expression, and this nonlinear piece is a feature of the non-abelian gauge theory. So in this case, with the gauge fields along the x and y direction in spin space, the gauge curvature turns out to be in the z direction. So the two orientations of spin here are related by rotation about the z-axis. So let me summarize the similarity, the analogy of this with general relativity. So in general relativity, you have the 4-vector of velocity of a particle moving in space. And in this theory, the object that's similar to that would be the magnetization vector m with 3 components. So what amounts to an accelerated motion in some inertial frame in general relativity corresponds to twists of magnetization. The Levi-Civita connection, or the Christoffel symbols, gamma I, j, k, have a relative in the spin connection of the gauge field, SO3 gauge field, and the Riemann curvature corresponds to spin curvature. So basically, you can see that they have the same number of indices, except in general relativity, all the indices are spatial. Roman indices, and in chiral magnetism theory, Some of the indices are spatial, and some of the indices are spin indices. Okay, so that's the difference. Another way to look at this is to ask what your theory, what kind of transformations leave your theory invariant. And of course, for exchange interactions, the symmetry of global spin rotation is the symmetry. So here we'll adopt the passive view of transformations. So we're going to do a rotation of the spin frame. The spin X is alpha, beta, and gamma, say, can be rotated in space. And if you rotate them by an infinitesimal angle omega, the vector components will change according to this equation. So that's what I will call spin vectors. These are collections of 3 coordinates in spin space that change as specified by this equation under a rotation of the spin frame. So examples of spin vectors would be just spin itself, magnetization, and spin current moving along some direction in space. So Heisenberg exchange interaction, which is grad M, will be invariant under global spin rotations or spin frame rotations, but they will not be invariant if the spin rotation is local, right? So if you twist your spin frame at one point a lot and at a neighboring point you don't twist it at all, then the gradient of magnetization will change in a non-trivial way. So in other words, although M itself is a vector, the partial derivative is not a vector because you're mixing spin components from different spatial points. In order to generalize the notion of the derivative so that the result is a vector, you have to introduce this covariant derivative, which includes the gradient as well as a cross M term. And so if you can check that this quantity does transform like a vector in this way, provided that the gauge potential A transforms like so. So here you can sort of see that it's similar to gauge transformations of our beloved electromagnetism theory, except here you differentiate the vector and it's a covariant derivative, whereas in electromagnetism you would differentiate a scalar function to get a gauge transformation. And so this tells us that the regular gradient squared is not an invariant energy density under local spin transformations. And so if you want to make it invariant under both global and local spin frame rotations, this is the form it should take. So you replace the regular derivative with the covariant one. So you can take this expression, remember what the covariant derivative stands for, and then you can just expand this in the powers of the gauge potential A, and you'll have 3 terms, the first of which will look like the regular exchange. The next term will be basically the form of the Teleshinski-Mori interaction, in which the role of the gauge field is played by the Teleshinski-Mori vectors. So that's really a very stunning revelation to a theorist like myself, that the DM interaction is nothing but a background gauge field. And immediately you start having all kinds of questions. So DM interaction is not really a physical quantity, it's gauge dependent. Okay, so that's an uncomfortable thought, but that's how it is. In fact, you can eliminate a DM interaction along any direction by just twisting the local frame so that the spin parallel transport looks trivial in these twisted frames. Now, there's finally a third term here, which is second order in the gauge potential. It looks a bit weird, but you can, in fact, reduce it to something simpler. You can just use a vector algebra to express it as an anisotropy term plus a constant. And so what this does, it just gives you some easy plane anisotropy in a thin film. And in a system with cubic symmetry, this just reduces to a constant. So historically, the gauge invariant or covariant formulation was introduced, in fact, way back in 1978 by Teleshinski himself and Volovik. It then resurfaced in the 1990s when Larkin visited Piers Coleman and Chandra and Rutgers. And again, there was a very underappreciated paper by Aharoni, Anton Wollman, and Shechtman in 1992, where they discussed the weak ferromagnetism in lanthanum cuprate. A similar perspective, in fact, also exists in the theory of itinerant magnetism, which was introduced by Froelich and Studer in 1993. And I learned about it from a very nice paper by Tocatli, who calculated the equilibrium spin currents using this SU2 version of the gauge symmetry. So these people use SU2 gauge theory, and these ones SO3 simply because they apply to different objects. SU2 is applied to spinor wave functions. SO3 is applied to just magnetization vectors. So in a minimal model of a chiral ferromagnet, we have the gauge potentials given by the DM vectors. You can just look up Bogdanov and Yablonsky to see what the DM vectors are. And so we know what the gauge fields are for different symmetry classes of various compounds. So if it's substantially symmetric, then the gauge fields just point along the corresponding directions in a thin film or orthogonally to that. And in a D2D symmetry class, they can point along one of the direction and against the other of the direction or something like that. So D2D is where anti-skyrmions have been found. Right? So that's the class of compounds. So let me give a couple of specific applications where you can see that this perspective is very nice. So we can start with the extension of the spin conservation law to spin-orbit coupling. So where does spin conservation come from? It comes from the symmetry of global spin rotations, right? So if you change the magnetization by rotating the spin frame, then the energy density remains unchanged. And so this results in having a conserved global quantity, which is the total spin along X, Y, and Z directions, and also a local conservation law, which is the conservation of spin current, which is shown here. The time derivative of the spin density is given by the divergence of a spin current, and both the spin density and the spin current are now vector quantities in spin space. They have three components. This equation can be derived from the equation of motion, the Landau-Lifshitz equation, which for the case of exchange interactions reads this. The derivative of magnetization with respect to time is given by m cross the Laplacian of m with some constants omitted here. So directly from this, you can express the Landau-Lifshitz-Gilbert equation, or Landau-Lifshitz here equation, as a conservation law if you identify the current with this expression here. Okay, so you just get exactly this if you identify J as minus m across the gradient of m. Okay. So the spin current is conserved as long as you just have this global rotational symmetry. And of course, it's violated once you add anisotropic interactions such as DM. DM is anisotropic in spin space. So if you add DM interactions, there'll be an additional DM torque on the right-hand side. And so you will end up with the conservation law broken already at the first order in V over C. First order relativistic correction will violate the spin current conservation. However, if you take the geometrical viewpoint, we now know how to generalize the invariance with respect to global rotations to invariance with respect to local rotations. You just have to switch to covariant derivatives. And then covariant derivative is basically just has more or less the same properties as a regular derivative. So you can just replace the regular derivatives everywhere by the covariant one. So this is your modified equation of motion, the Landau-Lifshitz equation for the gauged version of the Heisenberg model. And from that, you can again derive the conservation of spin current and the only changes are in the spin current itself. You've replaced the regular derivative with a covariant one, and you do the same thing in the spin current conservation law. So you can add further anisotropies, but typically further anisotropies would be of the second order in the relativistic parameter V over C. And so your spin conservation law will be spoiled, but not on the first order in V over C, but rather at a higher order. So that's the advantage of this perspective. You can see what you should do if you have additional chiral interactions just beyond the pure Heisenberg model. In this case, you can incorporate the relativistic spin-orbit coupling or the diameter actions quite naturally into this. Save the spin conservation law, so to speak. Okay, so another application is there were recently works, both theoretical and experimental, on generating diameter action by passing a spin current. So here, you can summarize this in the following terms. If you pass a spin current of strength Ji along direction I, then it generates a Teleshinski-Mori coupling for the same direction of the strength proportional to Ji. So these vectors are parallel. However, if you think about this from the perspective of this theory, it doesn't quite compute for the following reason. So as I mentioned before, J, the spin current, is a vector because it transforms under local rotations just like a vector should. However, the strength of diameter actions is not a vector. So it's a gauge potential. And the analog in general relativity would be the Christoffel symbol. Although it looks like a tensor with three indices, it does not transform like a tensor. So here it's the same thing. Christoffel symbol is an affine connection in general relativity, and here the Teleshinski-Mori coupling or the gauge potential is a spin connection. It does not transform like a vector. It has a different transformation law. So in addition to the usual vector thing, it also has an additional term, which is the gradient of the spin rotation angle. Therefore, a linear relation between spin current and Teleshinski-Mori term is not a gauge invariant statement. So it really depends on which gauge you use, that is on what sort of reference frames for spins you use. This is not necessarily an indication that this is wrong, but it's just an indication that you have to formulate things a little bit more carefully. There's a well-known analogy in superconductivity, which was pointed out to me by my former student Yuan Wan. The London's equation has a direct proportionality between the electric current and a gauge potential. And so, of course, this equation only holds in certain gauges, but it should not hold in every possible gauge. It's not that it's wrong, but it needs to be formulated perhaps in different terms. And there's an underlying theory for how this London's equation is obtained, and so one could have a similar bout of philosophical thinking in this theory. So perhaps, so it's 28 minutes, and before I dive into the more technical part of the talk, maybe there are some questions that people have about the previous parts. Or shall we just move on?
Maybe there's a couple of questions if you want to answer them now. Yeah, let's see. Let me get Nicholas first to ask the question. It's okay to ask now. So go ahead, Nicholas, ask a question.
Hi. So thanks for the talk. And yeah, one question is, you said that you can basically gauge away the Teleshinski-Mori. But if I imagine I have some finite spin current on a closed loop, then I can't gauge it away, right? Then I can't.
Right. Exactly. So just like a U1 gauge, you can gauge it away along some line, and usually not a closed line. If it's a loop, there's an invariant quantity, gauge invariant quantity, which is the flux through the loop. And if the flux is non-zero, of course, you cannot gauge it away. The same thing applies here. So you can gauge away a Teleshinski-Mori interaction along some line, which doesn't end anywhere and does not close on itself, but you cannot gauge it away along a loop or generally along a set of lines that intersect.
Okay, so if there's some, I don't know, zigzag or Nell order, then there's basically no Moria allowed, right? Because then I have these, it's a 2D, let's say it's a 2D system, but still I have these lines and I can't find a loop where I get finite flux, right? So this means for the system there can't be no anisotropy. Is this right?
So it depends. If you know the gauge potentials, you can see whether the curvature partial I AJ minus partial JAI minus AI cross AJ. If this curvature vanishes, then you can always gauge away the DM interaction by choosing a reference frame.
Okay.
Let's move on to the other one quick question again from Adam Lavi.
Yeah.
Go ahead and ask your question.
Yeah. Hi, Oleg. So I just wanted to understand better that you mentioned in the beginning that the spin connection was non-abelian. I just wanted to know, not very familiar with the field, that what was giving rise to this non-abelianness, and because we
rotations don't commute, right? So
okay.
The rotation group SO3 is non-abelian.
Okay.
Strictly in that sense.
Okay, thanks.
Okay, let me take one more, and then the rest of them I'll put it for. So Igor, did I allow you to talk already? No, not yet.
Okay, now
Igor, can you go ahead and ask your question?
Yes. Actually, this is probably very primitive question, very simple. But when you were showing how Teleshinski-Mori and anisotropy appear, that looked like there is a specific connection between them. They're proportional to the same vector A, just one is squared and the other in the first order. But in real life, those are unrelated. How can you explain?
Well, okay. So in real life and in the Sun City, these are two different things, as we Russians say. So if you take the simplest model of the DM interaction, that is, you start with the TJ model or something like that, and you add spin orbit coupling. In fact, as Aharoni and his friends showed, you get exactly this kind of anisotropy that appears. And it's not a surprise because, in fact, the theory of itinerant electrons can also be cast as a gauge theory with an SU2 gauge field. And so if you integrate out those electrons and just work with local spins, you end up with the precise SO3 gauge theory. And so the anisotropy in that theory would be exactly the square of the DM couplings. That said, you can have other sources of anisotropy, like just for example, dipolar interactions, which don't fit into this frame. So yes, in real life, the anisotropy can be different from the anisotropy that's obtained in the minimal gauged Heisenberg model.
Okay. Also, the symmetry restriction is weaker, correct? Because there can be bonds where Teleshinski-Mori is not symmetry allowed, but anisotropic coupling, exchange coupling is, right?
Well, they have different symmetry. That's true. One is a vector and another is a tensor, so there can be different requirements there.
Okay, so let's move on.
Thank you.
By the way, you're talking about Avant all the time. He's on the audience.
All right, so back to the chiral ferromagnet. So how can this perspective, the geometrical perspective, help here? So this line shows the Landau theory of a chiral ferromagnet, which has exchange, which has the DM term, as well as some quadratic term for stability and the Zeeman coupling. And as Flatterer's group showed, if you just try to minimize this free energy, your A phase always loses to the conical phase. And you have to invoke thermal fluctuations around the mean field solution to justify the presence of this Skyrmian crystal. So it turns out that the Heisenberg model, which is gauged, offers the simplest, perhaps, analytical route to a Skyrmian crystal. And that's what I'm going to show in the remaining time. By the way, Hira, how many minutes do I have to finish this before the discussion?
Oh, until the end of that. I mean, you still have 25 minutes.
25 minutes.
Because
Perfect.
you've been taking some questions, so it's fine to.
That should be.
I'm sure you're having time.
Should be enough. Yes. Good. So let's go back to the work of Belevin and Podakov of 1975. A beautiful 2-page paper with 3 references that everybody quotes, but very few people actually read. It's a really nice paper. This is the energy density of the Heisenberg model. If you want to find the energy minima, you take the functional derivative with respect to m, and you end up with the Laplace equation, which looks deceptively simple, but in fact it's not. It's not a linear equation because there's a constraint on the length of spin. M has to be 1 everywhere in magnitude. And so finding states that are local energy minima satisfying this equation is far from trivial. You can easily find the ground states where magnetization is simply uniform, but that's about it. And so Belevin and Podakov found a way to get additional local energy minima, which are stable for topological reasons. And this is what we call now the Bogomolny equation. So if you find configurations that satisfy a first-order differential equation like this, you can show that the energy of these states is a local energy minimum, and the energy is given strictly by the topological charge, in this case, the Skyrmian number. Topological means that you can perturb this configuration slightly, but the topological charge will not change. And so the energy, in fact, will not change if you make these small perturbations. It's really remarkable. And so the energy turns out to be plus or minus 4 pi q, depending on whether you choose the plus or minus sign in this first-order Bogomolny equation. They solved the Bogomolny equation by switching from real space coordinates to complex coordinates, and from the 3 components of magnetization to complex fields psi and psi bar. And so you can reformulate the Bogomolny equation in terms of these complex fields and coordinates, and you get a stunningly simple equation that the derivative of the field psi, either with respect to z or its complex conjugate z bar, has to vanish. And so it means that psi is independent of either z bar or z, so it's a function of z or z bar. Any analytical function of z or of z bar, or in fact any meromorphic function will do. So what's the difference between analytic and meromorphic? Well, analytic is well defined everywhere, and meromorphic may have isolated poles, okay, like 1 over z, for example. And so that's what they did. And a pole, in fact, corresponds to, or a 0 corresponds to the center of a Skyrmian, as you can easily find out. And so for the solutions that are meromorphic or holomorphic, as people sometimes say, functions of z, you basically have the Skyrmian number equal to the number of zeros or the number of poles, whichever you prefer. And so the energy ends up being just 4 pi times the number of these Skyrmians. And Skyrmians just become ideal particles because independently of the distance between them, independently of their radii, each Skyrmian just adds the energy of 4 pi to the system. So these are really ideal particles in the 2-dimensional Heisenberg model. Or you can use the other solutions, the anti-holomorphic solutions, or anti-meromorphic, whatever you want to call that, z bar instead of z. And the Skyrmian number would be just negative of the number of these zeros or poles. And the energy would be negative 4 pi q. And so it's still 4 pi times the number of these anti-Skyrmians. So here I beg forgiveness before the audience for using non-standard terminology, because anti-Skyrmians in this talk means particles with the Skyrmian number of -1. I am well aware that since an unfortunate incident due to Nagaosa, what's called anti-Skyrmians is really Skyrmians that look like anti-vortices, right? In the D2D symmetry systems. But for the purpose of this talk, an anti-skyrmion is a skyrmion with charge -1. Okay, just bear with me. Okay, so that was the simple Heisenberg model as we know and love it. And now we're going to see what happens in the gauged version of the Heisenberg model with a non-trivial gauge field that has a non-zero curvature. One of these symmetry classes that I've considered would fit the bill. Again, this is not my idea. I'm basically spreading the word. But the first works that analyzed this theory are due to Schurz in the UK, who is a mathematical physicist who has a series of beautiful papers on this, where some exact solutions have been constructed along the way, along the lines of Belevin and Bonakov. So here it's the same story. What we do is we try to minimize this energy. And instead of Laplacian m being 0, we have Laplacian in the covariant form m minus h. You have to add a magnetic field of the same strength as the gauge curvature in order for this theory to be solvable. So it's not a zero field, but it's in a specific value of a magnetic field, which you can think of as some critical magnetic field. And if you have a question of what the critical means, I will explain that in the Q&A. So you can solve this exactly by finding, again, solutions to the Bogomolny equation, which shows up here with the simple replacement of the regular derivatives with covariant ones. And then you can show that the energy of the theory with the correct Zeeman term ends up being, again, up to the Skyrmion number, plus a boundary term. And this boundary term has to be there for gauge invariance reasons. And fortunately, it can be ignored if you are in the thermodynamic limit. So it means that the energy of the system is proportional to its size. And so a boundary term would give a negligible contribution to the energy because it's only proportional to the perimeter, not the area of the system. So here are different symmetry classes listed in the Bogdanov and Yablonsky paper, and you can find what the Bogomolny equations look like in them. They're similar to the Bogomolny equation of the regular Heisenberg model, except there is this Teleshinski-Mori strength kappa that shows on the right-hand side. So instead of 0 here, you have something non-zero. So your Bogomolny solutions would involve a holomorphic function of z or z bar, and then an anti-holomorphic part proportional to the strength of the Teleshinski-Mori coupling. So again, that was first noted by Schurz and collaborators and unbeknownst to us. So we were basically doing a similar thing, not knowing about their work. Now we do. So you can solve these and for the holomorphic function w of z, you would normally get Skyrmion numbers that are all positive, depending on what this function is, how many zeros or poles it has. But the presence of the anti-holomorphic linear part z bar makes it possible to have a Skyrmion number that goes into the negative territory. And that's in fact crucial, because if you now think about the possible values of the energy, you can have the vacuum with the 0 energy, but you can also have positive energies with 1, 2, 3, and so on skyrmions. But in addition, you can have an anti-skyrmion or -1 skyrmion, and then the energy of the system will turn negative. And of course, if you're searching for ground states, the lower the energy is, the better. And so we should pay attention to this -4 pi energy and see how that could help us. So that's what a single anti-skyrmion looks like in this theory. It just looks like a regular anti-skyrmion or a regular skyrmion if I use the standard language, and it just has a skyrmion number of -1. Okay. So if we can have the skyrmion charge of -1, can we have skyrmion charge -2, -3, -infinity? So that the energy would go all the way down to -infinity. And the answer is not with the Bogomolny state. So these exact solutions basically only apply to Qs starting with -1 and going up. And you cannot go down, unfortunately. But we're not mathematicians, we're physicists. So let's try to be practical. I know it's funny coming from a theorist, but let's see what we theorists can suggest. So we can start with the vacuum, which has no skyrmions, and so the energy would be 0. And then we can add one anti-skyrmion, skyrmion number -1, and then the energy would be -4 pi. So that's a good starting point. We know that that's an exact solution. But suppose we add 2 anti-skyrmions, right? So one here and one there. If they're sufficiently far apart, and by far apart, I mean farther away than the characteristic wavelength of a skyrmion crystal that will come out in this theory, that characteristic wavelength is set by the strength of the Teleshinski-Mori coupling. So if these guys are far apart, then they barely interact with one another. They do interact a little bit, and it's not an exponentially decaying interaction. It's a power law, but nonetheless, you can pull them apart and they will interact weakly. So each of them will contribute energy -4 pi, -4 pi, to a total of -8 pi. Now, of course, we can keep doing that. We can keep populating the system with more and more anti-skyrmions, and as long as they stay far apart, the energy would be just -4 pi times their number. Something like that, okay? So one can, in fact, come up with a function, a trial function in this case, not an exact function, not an exact state, that would have the properties describing a bunch of anti-skyrmions in different positions. So how about that? And when these guys stay far apart beyond the skyrmion radius, then the energy would indeed be going down and down and down. Mathematically, you can ask, so what is a function that is periodic? We are constructing a skyrmion crystal, right? And so it has periodically spaced poles, and the name of the game is the Weierstrass zeta function. So you can open up some mathematical textbooks and find out about the properties of this function. It's actually not periodic, it's quasi-periodic. So if you shift by a period, you get back the same function plus a constant. So in fact, you can fix that specifically for a chiral ferromagnet by adding some term that's linear in z bar. And this function would be strictly periodic, and I'm illustrating it here. This is a plot of a complex function where the color indicates the phase, and black means 0, so the zeros are here in the corners of the hexagons, and white means infinity. So here, at the white spots, magnetization will point, let's say, up, and at the black spots, it will point down. And so you have something that looks like a skyrmion or something like that. So you can figure out everything about the interactions of these anti-skyrmions, which vanish as they go to infinity from one another, but then they start interacting as they get closer. So for 2 anti-skyrmions some distance apart, the interaction is inversely proportional to the distance squared with some logarithmic correction. And so you can figure out what the energy density would be for an anti-skyrmion crystal. The presence of these repulsive interactions means that you cannot populate the lattice with anti-skyrmions forever. When they start to crowd around, they will start interacting. And so the reduction in the energy brought by the negative self-energy of -4 pi will eventually be compensated by the energy of interaction. And that will be the energy density. So there will be a term that goes down linearly as rho is made negative, but there will be a balancing term that goes up as rho squared. So at low densities, the energy will go as -4 pi times the density of anti-skyrmions, but eventually it will curl up, and so you'll have a minimum somewhere. So this graph illustrates how we expect the energy to go. With skyrmions, it's just a linear function. The energy density is proportional to the density of skyrmions. They don't interact. With anti-skyrmions at low densities, they don't interact, but then they start interacting. And so there's an energy minimum, energy density minimum at some point, which we can predict, and which is borne out by Monte Carlo simulations. So there is an optimal lattice constant, which you can infer from this theory, which is about 8 inverse Teleshinski-Mori constants, and the energy is quadratic and negative in terms of the of this constant. And so here is a picture of the anti-Skyrmian crystal that obtains. This is an idealized representation just based on this trial function. And if you do Monte Carlo simulations, basically these guys are results of Monte Carlo simulations. So they differ, in fact, very little from the trial function. So it's a particularly a good guess. The dots that you can see here, some of them are Monte Carlo simulations, and the black dots are basically a theoretical prediction, as well as the curve are theoretical prediction. Okay, so that's the story so far. The chiral ferromagnet, we've reformulated it as a Heisenberg ferromagnet, just pure exchange, but with curvature and parallel transport of spin. And in this theory, DM vectors interestingly play the role of the spin connection of the SO3 gauge field, and that is in itself a beautiful, beautiful factoid for theorists. So it can be gauged away for certain directions, although not for all. If the gauge curvature is non-zero, then you cannot gauge it away by choosing a reference frame in which the magnetization will appear to be uniform in the ground state. So the advantages of this approach is we can redefine conservation law for spin current to just include the effects of spin-orbit coupling, at least to the first order in that coupling. And so the violations of the spin conservation law will be much weaker of the second order in the over C. The gauge Heisenberg model in 2 dimensions gives a nice, almost solvable model along the lines of Belevin and Potakov's 1975 paper that tells us that the ground state of that chiral ferromagnet in the magnetic field has to be an anti-Skyrmian crystal. Interestingly, if you change the strength of the field, remember I did this for just some magic value of the applied magnetic field. For lower values of magnetic field, you still retain the anti-Skyrmian crystal. And as you cross zero strength of the field and into the negative territory, the anti-Skyrmian crystal switches to a Skyrmian crystal. Not a surprise, because Skyrmians and anti-Skyrmians are related by time reversal symmetry. And of course, if you flip the direction of the field, that's equivalent to a time reversal. So that's the, so we have a good variational configurations that reproduce fairly well the results of Monte Carlo or vice versa. So it's a nice perspective, I think. It's pedagogical at least, and it's well worth using because sometimes it reveals interesting questions about physics. So I think I'd like to finish my talk here and thank the audience for attention. And I'm ready to answer questions.
Thank you, Oleg. That was fantastic. Thank you all the 275 people that showed up. So that's quite an audience that you brought in. So we have quite a few questions. I'm going to, people that have questions, maybe put their hands up or write the questions down. I'll go a bit on the order that they were stated here. So Ioannis, can you go ahead and ask your question if you don't mind?
Thank you. Thank you for the very nice talk. So the question I had was about the torsion of the SO3 gauge field you are using. So because you are working in 3 space dimensions, you can define something similar to torsion in general relativity using the SO3 gauge field. So have you thought about that?
No, perhaps we should have a discussion about that. So I've not explored that part. So here, as I said, the gauge curvature is similar to the Riemannian tensor. That's the equivalent. Torsion I have not thought about, but perhaps we could find a time if you could contact me and we could discuss this.
Okay, thank you.
Great. Let me see. Let me ask. Igor, did you have a further question, by the way? Yeah, you had
Yes, yeah, it's also another very simple question, but maybe useful. You know that obviously in real life, again, in real life, spin spirals very often appear without any relativistic effects, just from a frustration of different Heisenberg interactions. So in your continuous language, that would be like including higher derivatives of the magnetization. So is that a completely different ball of games, or it can be related to what you are talking about?
No, it can be used there as well, although you don't need to introduce the gauge curvature in this case, because it appears even without that, as you mentioned. And of course, there's a physical difference between spirals in the chiral ferromagnet and spirals in the frustrated ferromagnet, because in one case, parity is a symmetry, and in the other case, it's not, right? So you have twice as many ground states in the non-chiral case. But in fact, the geometric picture can be used regardless. In fact, the original paper of Teleshinski and Volovic was not about chiral ferromagnet. It was about spin glasses that have some weird ground states. So they just wanted to use a local reference frame for spins. So, if it's useful, it can be applied as well.
Yeah.
Matthias, you have a question?
Yeah, so thanks, Oleg. I have one question concerning this part number 5, where you discuss the current-induced DMI. So I just one comment and one question. So the comment is that in our experiment that you cite, we actually do not see a linear dependence. We see that the DMI, firstly, has the same dependence for both current directions, and secondly, it's clearly non-linear, so it doesn't go through 0. So in that sense, we kind of agree that it's not linear. But now the question is, I mean, do we learn anything from the different transformations? And is there any possible relation between the DMI vector and the current density that is gauge invariant, so that we could compare that to the experiment?
That's a good question, and that needs to be worked out. I mean, knowing the properties of transformations, of objects under transformations, simply tells you whether or not these two objects can be linearly related, right? Just like in general relativity or in special relativity. And once you realize that these two cannot be generally related by that, you have to just find the right covariant formulation, and then you can start.
Okay, so if you have any relation, let us know. We're happy to test it.
Yeah, so that should be worked out, and we'll do that and let you know.
Okay. So Jeffrey, go ahead and ask your question.
So in your theory, the examples you showed were for block type anti-skyrmions, but I was wondering if you wanted Nail type skyrmions or anti-skyrmions in your notation, would that be just a change in parameters, or?
Exactly. So I showed a table in which I gave the 3 symmetry classes. Right, so this was for DN. For DN, you just get Nail skyrmions, in fact. For CNV, I think you get block skyrmions. And for D2D, you get anti-skyrmions that look like anti-vortices. So all these theories can be used. It's just a slightly different choice of the gauge fields. So it all can be treated on the same footing.
Okay. Thank you very much. Really enjoyed your talk.
Thank you.
Igor Tchernyshyov, go ahead and ask your question.
Thank you. So Oleg, what's about fluctuations about this Belayan-Polyakov type solution? So as I understood this, your Monte Carlo numerics that you showed seems to suggest that fluctuations are not really large, because you have good comparison with your trial function. But is it clear what parameter controls fluctuations?
Well, this was a classical Monte Carlo done at a very, very low temperature, so fluctuations really should be weak.
No, I meant in theories.
We're dealing with the ground state. Yeah, no, but what sort of fluctuations are you talking about, Igor? Thermal fluctuations, quantum fluctuations?
Quantum.
Well, it's a classical Monte Carlo, and it's a classical field theory, so there are no quantum fluctuations to speak of. It's classical magnetism.
Okay.
Okay. Revas, go ahead and ask your question, please.
Thank you. Hello, Oleg, and thanks for the talk. There is, I mean, there has been this general discussion about the spin current and, you know, as a non-conserved quantity, and there were certain question marks raised by various people, including Emanuel Rashba, sort of various warnings, because, you know, if you have a right-hand side in the continuity equation, then the entire current is not that well defined. And, you know, I heard opinions that, oh, the best thing is to calculate the observable quantities without even turning to spin current, just as a means of calculation. So from all the thought that you gave to this issue, to spin current that you mentioned quite a few times, what is your perspective on this?
Right. Yeah. So my perspective is, if you just use the standard theory with the global spin frame and no gauge fields, you find that adding spin orbit couplings or DM couplings, which are basically consequences of spin orbit couplings, you find a violation of the continuity equation to the first order in DM, or spin orbit coupling, or V over C. And that, of course, is bad. However, if you adopt the gauged perspective, you can neatly package that violation that comes from the first order DM term into the redefinition of the spin current and of its conservation law, which is just made through covariant derivatives. And so then residual anisotropies, which are of the second order in V over C, will still spoil your spin conservation, but they will spoil it much less. So at least qualitatively, this looks like the concept of spin current and its conservation can be made more useful because it's more long-lived than the original concept.
Okay, thank you. I guess this is something to think about.
Yeah.
Thank you.
Yeah,
go ahead.
In fact, it's not the first time people thought about it, right? So I mentioned,
of course not.
Tocatli's paper, which was an inspiration for this.
Yeah, well, and before Tocatli, long before, like there was a discussion by Rashba, and
by many,
by many, precisely.
Right, yes. But that's way out through the gauging of the theory. I think that was first done by Tocatli. That's a really beautiful paper.
So Alexander, go ahead and ask your question.
Hello, thank you very much for a very nice talk. Just out of curiosity, what would be, let's say, if you would add like an electrodynamic FF term and would consider this gauge field to be a dynamical field, what would it be? What would it correspond physically to?
Good question. We have not done that. We have not considered the dynamics of the gauge field itself. I can again point you to the paper of Tocatli, who in fact calculated the equilibrium spin currents, for example, for the case of Rashba and Dresselhaus spin orbit couplings in a 2D film. And he showed that you can express the energy of that system as effectively the Maxwell term Fij. And from that, he derived where F is literally this gauge curvature. And so he was able to derive the equilibrium spin current from that, knowing the coefficient of that Maxwell term. So it's not just about the dynamics of the gauge field, but it's also about equilibrium spin currents and whatnot. So yeah, that's a direction to look into. And I'm of the opinion that I shouldn't do everything myself. I prefer to open up directions and see if people can take them up. And that's the greatest recognition.
That's a wise idea. So Marcus, go ahead and ask your question.
Yeah, okay, so thanks for the talk.
Can you express spin transfer torque or spin pumping in the geometrical formulation, and how would that look like?
Wow, really great question. I've not thought about that. I've thought about the spin transfer torque in a completely different mindset, but that's a subject for another talk, I think. So spin transfer torque is an instance of a gyroscopic or gyrotropic force, but again, that's a story for another day. No, I've not thought about that, and I mean, sure, it can be pursued that direction.
Okay.
Thank you.
Helen, can you go ahead and ask the question?
Yeah, thank you. Oleg, it was very nice to see you once again.
Likewise.
After a year of. So my question is very naive. As far as I remember, these meromorphic functions we find in this Polakov theory of the branching domain structure in ferromagnets. So as you use the same mathematical tools, do you think that these skyrmionic lattice should also have some kind of fractal behavior at some scale?
In fact, I think this direction has been pursued by our friends Filipov and Rybakov, who teamed up with Schurz and company, and they recently had a paper about, they constructed some beautiful chains of skyrmions that bunch together using, you can construct lots of meromorphic functions and play with them. However, if you construct the skyrmionic ones with positive skyrmion numbers, the energy is just positive and proportional to the number of skyrmions. So these are highly excited states, which is okay in the spintronics, right? We deal with domain walls, which are not ground states, which are topological excitations. And so yes, you can do that, and you can do so profitably. But our goal here was to find the ground state, and so we had to go in the opposite direction. Instead of going, adding skyrmions, we had to add anti-skyrmions, as I call them.
Okay.
Thanks.
Christina, go ahead and ask your question.
Hello, thank you for your talk. As far as I remember from the Bedlavin-Polyakov approach, since the energy functional is scale invariant, the particle does not have a definite size. So if then you proceed and analyze a Zeeman term, for example, you would get some logarithmic divergences that are usually fixed by introducing a cutoff. Is that relevant in your approach, or do you see something like that?
Okay, so you're right. The Heisenberg model proper is scale invariant. However, once you add the DM term, you're injecting a length scale. Right? The strength of the DM term dictates what the wavelength of the spiral or the period of a skyrmion crystal would be. So there is a natural size then for your skyrmions or anti-skyrmions to have. Even with that, a single anti-skyrmion solution or skyrmion solution will be will have these power law dependencies, right? You construct something like 1 over z, for instance, or 1 over z plus some linear term z bar. And so you can find that there are these infrared divergences, and sometimes you have to impose some large distance cutoff. Miraculously, all these problems go away if you add this Zeeman term with the strength equal to the strength of the SO3 gauge field. Then everything becomes finite. And generally, if you pack the system with anti-skyrmions, the ground state is an anti-skyrmion crystal. The energy is just proportional to the system size. We're in the thermodynamic limit, and so these problems disappear. But with single textures, yes, you can have divergences of the same type.
Okay.
Thank
you. Shivali, go ahead and ask your question.
Hi, Professor Oleg. Loved your talk. So I have a slight confusion actually. when you said that we can add more and more anti-skyrmion if they are far away from the coherence length of the skyrmionic crystal. So my confusion, if we take thermodynamic limit, won't the ground state go to negative infinity, and that would cause the states to become unstable?
Yes. So suppose you've placed one anti-skyrmion per square millimeter. They're sufficiently far apart. And then, of course, the energy of the state would be proportional to the number of these cells, right? And that's exactly what we mean by the thermodynamic limit. You have a finite energy density, and so as you calculate the energy of the system, it'll be proportional to the system size. However, the right question to ask is not what the energy is. Of course, it will be infinite in an infinite system. The right question to ask is, what is the energy density? And you have to minimize that. And so you find that the energy density at first goes down as you pack more and more anti-skyrmions. As long as they're staying far apart, it'll be just proportional to the density of anti-skyrmions and going down negatively. But you cannot make it infinitely negative, the energy density, because as the anti-skyrmions get closer to one another, as you pack more and more of them, they start interacting. And so there is a point where you go from further reducing the energy, you find the minimum, and then packing more anti-skyrmions doesn't work anymore, and the energy starts going up. So there's no contradiction here.
Okay. Thank you, Vladimir. Go ahead and ask your question.
Very exciting talk. Thank you. The question is the following: is it possible, based on your results, is it possible to formulate some instructions how to really build a curvilinear frame of reference where a DMI of given type disappear?
Oh yeah. What you have to do is, once you figure out what the gauge field is, then you can just go along a, let's say, straight line and twist your spin frame at exactly that rate AI. If you do that, then your Teleshinski-Mori interaction will be gauged away for that particular line. Okay. Now, if you imagine doing this along a line going in a different direction, you may be out of luck, because then you can make a whole loop, and it's not always possible to gauge it away around a loop, because there may be a non-zero gauge flux. And so for the Teleshinski-Mori interactions in these symmetry classes, the gauge curvature, or the SO3 magnetic field, is non-zero, so you cannot gauge away the Teleshinski-Mori interaction around closed loops. So you can only gauge it away for certain lines, for certain directions, but not globally.
So Yonko, go ahead and ask your question.
Hi, Oleg. Great talk. Great talk.
Hi, Yonko. Good to hear from you.
I have two small questions. One is it not so that the Teleshinski, the Teleshinski-Mori interaction is already second order in spin orbit interaction, which means it's V squared over C squared, just like magnetic anisotropy. And no, here you have all the effects are A squared. Am I mistaken? I'm trying to say, which is wrong, obviously, but I'm trying to say that these amazing effects are fourth order in V over C.
No. So DM is of the first order in the V over C.
It is. Okay. Okay. So the other question is, it's not so much a question, but something you can say for my edification. Your 2D examination of the crystal, it does feel a lot like a Wigner crystal, but I didn't have time to inspect the things you showed. Has the energy, for instance, does it look like something like in a Wigner crystal?
In fact, it does. So in a Wigner crystal, you have long-range Coulomb interactions, which are 1 over r in 2 dimensions. 1 over r in 3 dimensions. And if well, there's still 1 over r in a 2-dimensional thin film because it's embedded in 3 dimensions, right? However, yeah, and in fact, the interaction between these anti-skyrmions also behaves as a power law, but it's not 1 over r, it's 1 over r squared. So it falls away a bit faster, but it still is a long-range interaction. So yes, you can think of this as some sort of a Wigner crystal. And I think, or I might be mistaken, but no, I don't think so. I was trying to refer to the paper by Bogdanov and Yablonsky from 1989, where these skyrmion crystals were first predicted. I don't think they used the analogy with a Wigner crystal. They used an analogy with an Abrikosov vortex lattice instead, which also has long-range interactions in a neutral superfluid, but in a charged one, of course, they have a range.
Okay, thank you.
Yeah, but I thought that this would analogy in the 2D would be closer, a little bit closer to the skyrmion lattices observed, well, not observed directly, but induced by NMR in quantum Hall effect, right? In fact,
yeah,
the 2D version.
Yeah,
I've worked on this before.
Right.
I think Jung was my editor on that paper, I believe.
Oh, so you still hate me then?
No, I love you dearly. No, I got published. It was fine. There's no problem.
No, we love you, Yonko.
Thank you.
Definitely, very much appreciated. And the fact that you keep joining is very better. So, Nicholas, I think you're the last question left. Go ahead.
Okay. Concerning the slide we are seeing right now. So I think you said going up that to the right, you said that skyrmions don't interact. Why is that? I think I didn't quite get the difference between the anti-skyrmions and your anti-skyrmions.
Well, so the technical argument is as follows. If you can solve the Bogomolny equation, then you know exactly what the energy of your system is. It's just given by the topological charge. So if you construct a Bogomolny state with n skyrmions, then the energy of the system is simply 4 pi times the number of skyrmions. It doesn't matter how close these skyrmions are or how far away they are. So the energy just ends up being independent of those details. And that means that skyrmions act like ideal particles, each of which carries energy 4 pi, but it doesn't interact with any other skyrmions. That's why the red line here is a straight line. So if you just look at the energy density of a skyrmion crystal, it just goes up linearly. But not so with anti-skyrmions. There are no Bogomolny states that contain more than 1 anti-skyrmion for this value of the magnetic field. And if you construct one, you know that since it's not a Bogomolny state, the energy need not be 4 pi times n. So it need not be linear, and it turns out not to be linear. Of course, it would be a disaster if it were linear, because it would just go down to minus infinity. And that would be complete nonsense, right? You cannot pack infinitely many anti-skyrmions and expect a low energy.
I see. Thanks. Great talk.
I did lie. It was not the last one. So, Carlos, go ahead if you have a comment.
Okay. Hi, Oleg. Can you hear me?
Yes. Hi, Carlos.
Beautiful talk. Thank you. I'm always fascinated by this formulation in terms of vector potentials and gauge fields in condensed matter. And I as you mentioned already, people have done this, in the context of the Raja and Dresselhaus type of Hamiltonians, the quantum version. And you can elucidate a couple of things and view things more simply, as you said. Pedagogically, I think it's very important. You also mentioned the connection or the analogy with the London equation, and also in the mean field type of BCS Hamiltonian. We know that the gauge is fixed, and then you kind of have a breaking of symmetry of the gauge field, which leads to a non-conservation of the particle number or the charge. Now, have you thought about this kind of context in your problem, to think about possible conservation laws that are not being actually conserved? I mean, it's very interesting that someone asked about the connection with spin currents, right? That it makes it more palatable in the sense that it's more conserved. But at the same time, because the gauge is sort of fixed, and as I understood, it's it's related to the DM vector, right? The Teleshinski-Mori vector. You would not expect anything to be conserved. So can you comment on this, and perhaps in this connection with symmetry breaking?
Right. No, so the gauge need not be fixed. We just know what the by stating the DM interactions, we're specifying this for a particular gauge. And in this case, the gauge choice is dictated by what spin frame you choose. You just choose the global spin frame, and then your DM couplings are what they are. But you can change them by making a twist in the spin frames, right? So if you make a twist, then the DM interaction will be different. And that's what the gauge transformations are. They're just really local spin frame rotations. So in principle, you can change that. And the answer to your question is that the gauge need not be fixed, but what we can do is we can just write all of the equations in spintronics using a gauge invariant language, or gauge covariant language, shall I say. So we can just use whatever reference frame we like. And in fact, people have been doing that for a while, because, for example, if you think about the spin torque and go back to the beautiful paper of Bazali, Zhang, and Jones from the 90s, they were thinking about a local reference frame that simply follows the local direction of magnetization, right? So these things have been done, and you just have to think about it in the right mathematical terms, and this gauged version of the Heisenberg model is precisely what it is.
All right, thank you.
A very last question from Bruno, which is a student in the UK. Go ahead, Bruno.
Sorry, I'll try and be quick. Thank you very much for the talk. It was very very nicely expressed. I just wanted to quickly comment on that question of skyrmions acting as ideal particles, because I think it's slightly subtle, because there are these, they keep the same energy while you move them around in some way. But the interesting part is that you don't see in the solution skyrmions moving apart or together. So they're, in some sense, they do attract each other or repel each other or whatever, but you don't sort of see them as independent individual particles.
Suppose we take a solution that would be, the sum over 1 over z minus zi.
Mm-hmm. Yeah.
No matter where you put these zi's, no matter where you put the cores of these skyrmions, you get the same energy.
That's indeed true. That's indeed true. Yeah.
So it's in that sense that they're ideal particles. Of course, you can deform them. If you deform them beyond these neuromorphic solutions, the energy will change, right? Because the Bagamortin equations will no longer hold. And in that case, of course, you will induce some interactions. But in their most politically correct form, shall I say, they will not interact, right? And so you can construct ideal
with the presence of this additional term. It's sort of like they're moving around with this sort of additional part,
right?
This anti-skyrmion kind of hanging around, or how to put it.
Right. Yeah.
Okay. So I think with that, I would like to conclude for today. It's a wonderful talk, Oleg, as expected. You'll be proud to know that there were 290 people hearing you and watching you. So it's a nice format, a nice place to give talks. Yeah.
Absolutely.
I'm sure you'll be
love the questions, love the audience. Thank you.
Yeah, it's great. A great engagement. I never want to stop as long as the speaker can hold on and continue. I always